Today I want to convey across an idea on how we can get the students to be thinking about the trigonometric ratios in mathematics to help them sort of access higher level mathematics in the future. So we first of all need to think about our definition of what the trigonometric ratios are. Now most of you would have explored these by looking at a right angle triangle, and I certainly would have done to start off with. And what we would do is we would think about given some angle theta and some side lengths, let's just call them A, B and C, we would define these terms, sine theta, cos theta and tan theta, as ratios of the side length. So sine theta would be the opposite over hypotenuse, so in this case it would be B over C. Cos theta would again be the adjacent over hypotenuse, so that would be A over C, and tan would be the opposite over adjacent, so B over A. Now, what we've done here is we've defined our sine, cos and tan to be some ratios of a right angle triangle. So these are all defined as some sort of ratio, and that's great for what we need to know in GCSE mathematics. However, I want to try and persuade you with a series of logical steps as to why we can think about sine and cos in a better way, rather than thinking about them as just these stale ratios. So, in order to do this, I am going to first of all plot a Cartesian plane. So you can have a go as well, or you could use some sort of dynamics software. And a Cartesian plane is just your x and y coordinates, and I'm going to plot on a perfect circle starting at the origin. So starting at the origin, expanding out, and I've just drawn a circle. The main definition of this circle is that it's going to start at the origin, but I'm also going to make it so that it has a radius of 1. So from the centre to the edge, that would have a radius of 1 for some coordinate x, y, which is on the circle. If it's got a radius of 1, we would say it's a unit length. So this type of circle is often referred to as the unit circle. So I'm just going to note that on there. What's important to note about the unit circle is some of the key features are the intersection points on the x-axis and the y-axis. Along the x-axis it will go through at positive 1, and also if it's got a radius of 1, it'll go through at negative 1. Likewise, in the vertical direction on the y-axis, it'll go through at positive 1 and negative 1 respectively. So I'm just going to link all this together and just bring it over here. And what I want to think about is, what can I do with this circle, with this point, that has some relationship to this right angle triangle ratios? So, looking at this then, if I try and introduce a right angle triangle by drawing perpendicular lines for x and y, hopefully you can convince yourself that this is the case, as x along and y up would give me this coordinate xy. And if I take this triangle and just draw it in isolation, we've got y and x and 1. And I think about my trigonometric ratios, well, I would first of all need to define my theta. My theta I am going to define as the angle between the positive x-axis and some point on the curve, whether it be over here or over here. It's just defined as the angle between the positive x-axis and that point. So for my isolated triangle, it'd be theta would be here. So if I have a go writing out sine and cos, my sine of my angle is going to be equal to my opposite, which is y, over my hypotenuse, which is 1. And likewise I can do that with cos. I get cos of theta is equal to my x this time over 1. And if I really think about this, I'm dividing by 1 at each stage, which is going to have no consequence on my value of sine theta and cos theta. So therefore I could redefine my values of y and x to be equal to sine theta and cos theta respectively. So now instead of thinking sine and cos as some sort of ratio between the side lengths, I've got that my sine of cos are actually side lengths. they're no ratio at all. They are actually the size lengths of y and x on a unit circle. Now this is really, really powerful, because what this allows me to do is this allows me to think about my x and y coordinate, which I previously had, to actually be some sort of function. My x coordinate was cos theta, so therefore I can write cos theta as the coordinate, and I can also think about my sine theta. So what I've got here is I've got some point on a unit circle, and no matter where it is, whether it be over here, whether it be over here, I can define it as this idea of sine theta and cos theta, and they're no longer ratios, because cos theta now is going to be a function which will tell me how far along my coordinate is on the x-axis. And sine theta is also a function, but it will tell me how far up my coordinate is on the y-axis. So now I can think about these as trigonometric functions. This allows me to explore all manner of different things to do with trigonometry. Unlike with my ratios of side lengths, I can now explore what happens if I have a negative, because here it's going to be a coordinate of, let's say, negative root 3 over 2 and negative root 3 over 2 for cos and sine, which we wouldn't have been able to previously get by looking at side lengths of a triangle. We can also think about some of the bonuses for, well, let's think about our ratio for tan. So instead of now thinking about x and y here, we can think about it being cos theta and sine theta. So I'm just going to let this be C and let this be S, denoting cos theta and sine theta. I'm just going to define it up here. What would be my definition for tan? Well, my tan theta would be my opposite over my adjacent. Now if I look at this, my opposite over my adjacent, well, that's going to be my sine over cos. So I can pull out this definition quite easily, this identity rather, that my tan of my angle would be equal to my sine of my angle divided by my cos of my angle. And some students may be able to pull that out for themselves, and it would be a really good exercise to let them try and figure that out. And another thing we can look at, given that we've got a right angle triangle, and we've got a right angle triangle here, we can think about what happens when we explore Pythagoras in this situation. Well, again, Pythagoras, for two shorter sides, when we square them, will be equal to our larger side squared, the hypotenuse. So for this case, cos squared theta plus sine squared theta would be equal to our radius squared, which as the unit circle, it would be 1 squared. We know that 1 squared is equal to 1, so I didn't need to write that. And out pops another identity. Now these are really powerful and really useful to know as we go on to more advanced mathematics, and they can be used in all manner of different things. So I really hope you enjoyed this idea, and hopefully I've challenged the way you think about trigonometry, and it's not just to do with these triangles, but it's actually more to do with this idea of a unit circle and the coordinates on that. If you have any questions, or you want me to look at any questions or work that you've done, I'd be really interested in seeing how you found this, and you can find me at any point over email or even come and see me during school. Thank you very much for watching, and I'll see you in the next one.